exciting session coming up about individual fairness. The first talk is given by Professor Aaron Roth, who's a faculty.
The distinguished.
He's a distinguished professor from the University of Pennsylvania. He's going to talk about some exciting work with some amazing colleagues and myself.
All right, thank you, Stephen. So this is joint work with a bunch of students, former students, and now grand students. So with my colleague Michael Kearns, our current PhD students, Chris, who's right there, Seth, Stephen, who introduced me, who was our former student, who's now at Minnesota, and Stephen's student, Logan. So, okay, we're all here at a fairness workshop, so I don't need any motivation, but you've all seen these headlines. There's lots of justifiable concern that as we deploy machine learning algorithms in consequential domains, that they are exacerbating or perpetuating, unfairness, whatever that means. Okay, so it's easy to worry about this stuff, but definitions are tricky, right? So what does it mean that that something is unfair? And by and large, when you look at the academic literature on this, I would say there's sort of two major families of definitions. Okay, and I'm going to follow up a little bit on Sharad and others yesterday to first sort of beat up on what I'm going to call the sort of family of statistical fairness measures, and then talk about individual fairness. But first, let's maybe walk through how you might why you might like statistical fairness measures, right? Let's try to go through maybe an exercise, maybe in a lending setting, asking ourselves how we might what we might mean when we say that a classifier was unfair. And one way you might try to ask that question is by starting off and asking the question, who was harmed? Okay? Who was harmed by the mistakes made by the algorithm, the decisions of the algorithm? And one possible answer you might come up with is that the people that we feel were harmed were somehow the qualified applicants who were mistakenly rejected. Okay? And if that's the answer you come up with, then you might reasonably arrive at sort of this idea that maybe the false negative rate is something we should be interested in when we think about fairness, because if the people who were harmed were the qualified applicants who were mistakenly rejected, then the false negative rate seems to be the rate at which harm is done.
But there is a jump from the second sentence to the third.
Yes. So
identifying people that succeeded with being qualified.
That's right. And this is not going to be the thing that I talk about in this talk. But yes, so there are, so I'm not proposing that this is what we do. But this is sort of a popular definition in the literature that maybe we should try to equalize false negative rates across groups. And this is sort of just one of maybe a whole family of statistical fairness measures. If you want to come up with your own statistical fairness measure, here's the exercise you can go through. You can partition the world into groups, often according to some protected attribute, maybe race or gender. You can pick your favorite statistic of the classifier. It could be false positive rate or false negative rate or positive predictive value or just raw classification rate. There's a lot of these. And you can ask that this statistic should be approximately equalized across groups. Okay, so I would say by volume at least, this family of fairness definitions is by far the most popular in the academic literature, if you just look at the number of papers written about them. Okay, but there's sort of a number of reasons not to like definitions like this, sort of dating back to the catalog of evils from the Dwork et al. Fairness Through Awareness paper. And let me just sort of give a cartoon example of one of them. Okay, so suppose let's think again maybe about false negative rates and in a lending application, and we've got two attributes, two protected attributes that we care about, like race, maybe blue and green, and gender, male and female. And we say we want the false negative rates to be equalized across these groups, right? Men and women, blue people and green people. And suppose actually that the sort of labels that we're trying to predict are totally uncorrelated with either of these features. Okay, so there's a bunch of ways to make classification decisions to equalize false negative rates across these groups. Here's one of them, probably not the one that you wanted when you specified these constraints. I could give loans to people exactly when they are blue men or green women. Okay, that does in fact equalize false negative rates across race and gender. It's 50% in each row, it's 50% in each column. But that's cold comfort if you're a green man. It promises you nothing, like green men sort of deterministically are denied loans. Okay? So like, right, the problem is, like, by sort of very explicitly, right, these notions of statistical fairness only offer guarantees about the average behavior of a classifier over large groups. Like, that's how they're defined. They're constraints on averages over large populations. They're not constraints on individuals. And so, like, if you think about the meaning of these constraints, like what a statistical fairness constraint promises to you, it potentially promises you nothing, right? Like, if you're in one of these two quadrants, like, despite these fairness constraints, you are getting nothing. Right, and more generally, like, you can interpret them as a promise to you only if you sort of subjectively believe that you are a uniformly random member of one of these protected groups. Okay, so there are stronger sort of notions of fairness, individual fairness, again, dating back to this Fairness Through Awareness paper, that offer constraints that actually bind on individuals, right? Pairs of individuals rather than averages over groups that sort of get around this problem. Okay, and this particular fairness constraint tries to formalize the semantics that similar individuals should be treated similarly. Okay, and so like, it's defined a little bit more generally in that paper, but sort of one instantiation of that is that given some task-specific similarity metric D, given some way of measuring how similar pairs of people are for the task at hand, we should treat similar people similarly, which might mean, for example, that for any pair of people, the difference in probability that they, for example, are given a loan should not differ by more than their distance in the similarity metric. So in particular, like, if two people are at distance 0, if they're like equally qualified for the task at hand, they should get the loan, say, with exactly the same probability. Okay, so this is a nice family of definitions because it binds, and it's an individual notion of fairness because the constraint, like, explicitly binds on particular individuals as opposed to averages over people. Like, most of the problems that arise in the catalog of evils for statistical notions of fairness come from the fact that these statistical constraints are just constraints that are averages over large populations. Okay, so the immediate complication is that the metric here is like doing a lot of the work, and where do we get this metric? And trying to answer this question has been sort of the focus of a lot of the work subsequent to the original Fairness Through Awareness paper. Okay, so I want to sort of think about one way to sort of operationalize this, something that's not quite this, but in the spirit of this, where we want to sort of treat similar individuals similarly. Okay. So imagine that we impanel a group of AI ethics experts. Okay, so by AI ethics experts, I don't mean people that deeply, understand the problem. I don't mean people that have opinions you agree with. I just mean people who have opinions, people who, you can, like, ask questions like, do you think this pair of people should be treated similarly or not? And okay, so like, clearly this is going to be a contentious process. Like, it's hard to find groups of AI ethics experts that people will agree on. But I would sort of argue that, like, no matter what your proposal is to try to sort of implement some kind of measure of fairness, there's no avoiding some step like this, and that different people mean different things when they say, fairness in machine learning necessarily. And before doing anything, like, a necessary first step is to, like, figure out who you're going to listen to. Okay, so like, imagine that you get to choose who these people are. Okay, the people whose opinions you most respect for the task at hand. Okay, so what should we, like, expect from this group of people? So it seems, maybe too much to expect that the experts could, like, write down a fairness metric, that they could sort of express their conception of fairness as, like, a concisely defined quantitative metric. It's not even clear we should expect that their subjective judgments would even be, like, implicitly consistent with any metric. Like, maybe the problem is not just one of expressivity, but that, like, their sort of subjective notions of fairness are somehow, like, internally inconsistent. Like, I don't want to assume that there's any, like, triangle inequality, for example, here. And, if we have more than one person on the panel, it's sort of, it certainly seems unlikely that the experts would agree with one another in every case. Like, even if they could, like, express their notion of fairness in terms of some metric, probably they would have, like, different metrics. Still, we can imagine asking these people about particular case studies. So, for two particular people, and you can imagine giving them sort of rich information about them, maybe more information than the machine learning algorithm has access to, whatever information you want that you feel sort of correctly captures these case studies. You could ask them, should these two particular individuals be treated similarly? Where being treated similarly means something very precise. Like, should they, for example, be given the same label? Or should the probability that they're given a positive label differ by more, by like less than 10%? Okay. And once you sort of, even if you don't assume anything about how the people on this panel answer these questions, so you don't have to assume consistency with a metric, you don't have to assume that they agree with one another, there's nevertheless, like, already a well-defined trade-off to navigate. Okay, once we have a group of people who have opinions, it doesn't matter what their opinions are. Once we have a distribution over individuals, okay, there's two things we might care about. There's the classification error of the model we're ultimately training, and there's the frequency with which the classifier makes pairs of decisions that an expert views as unfair. Right? Like, once we have a collection of people who express opinions, and once we have a distribution over people and a classifier, then there is a well-defined rate over the sort of draw of two new people from the distribution that the classifier does something that causes someone in this panel of experts to complain. Okay? And so we can at least talk about this trade-off. How can we trade off the sort of error rate of our classifier with the sort of frequency with which it pisses off someone on our AI ethics panel? Okay.
The frequency with which there exists someone on the panel who is pissed off by a decision.
Yeah, so for the purposes of this talk, just to make things simpler, I'm going to imagine that the panel is just one person. But more generally, you could talk about, if you had, like, a very large panel, the sort of expected number of people on the panel who would complain, since they don't have this. So in the paper, that's sort of maybe the sort of more relevant thing. If it were a large panel, it would be the expected number of people complaining. But here I'm really going to just talk about, like, one person. Yeah.
So if your panelist has a particular classifier in mind, which they're not supposed to, but then they could simply say that these people are at 0 and those people are at 1, and the difference in the score is perfectly consistent with that.
They could, yeah. So sort of the motivating, the thing driving a lot of this work is the desire to, like, essentially make no assumptions about how the panelists are making their decisions. So that is certainly one thing they could do.
Sorry, so I had thought that the panel had an image of distance, But, so any given decision doesn't necessarily violate anything.
That's right. So I'm talking about pairs. So this is going to be a frequency over draws of pairs of people. Once I have a pair of people, I have...
Sorry, one difference doesn't matter. So it's like, I think, this person, I think that the distance between these two people is a half. So I expect, as any single time where my higher ranked person gets the goodie and the lower ranked doesn't, is fine. Any single time where the higher ranked doesn't and the lower does is also okay, because you expect that to happen some of the time. So
You're talking about after the
no, I just,
probabilistic?
You're talking about the difference between like the sort of randomization and the realization.
Yeah. So
I think you can...
pairs of decisions, that's already a random realization.
Yeah, so maybe for the purposes of the talk, let's think about the experts directly having opinions about and being able to observe the probabilities of positive classification, but
See the probability.
some of that, like since we're talking about sort of the expected number of times that the panelists complain, some of that sort of will wash out even if they only like complain about realizations. Okay, so let me talk about sort of the pros and cons of two different approaches to this. One that sort of is not something we're trying to do, and sort of there's reasons you'd want to do this, there's reasons you'd not want to do this, and compare it to what we're trying to do. Okay, so sort of one thing you might try to do is to sort of decompose this process into like a two-stage process. Okay, so basically, like first try to learn like the metric or the similarity function that the individuals on your panel are sort of implicitly making decisions with respect to. So try to sort of learn the metric, and then once you have this this object, this sort of metric you've learned, which you hope sort of what captures, the intuitive judgments of the panel in the sense that it will generalize out of sample, that it will sort of capture their beliefs about pairs that you haven't seen before, you could try to use this learned similarity function as a constraint. Okay, so that's not what we're trying to do. There are reasons to want to do this, though. I mean, the first is that there's a large literature you can draw on. People have studied metric learning. And there's sort of thoughtful recent work by Christina, who's over there, that you should read if you haven't yet, that sort of thinks about how you would make queries for metric learning to human judges, thinking sort of carefully about what kinds of questions are easier for human judges to answer. And the nice thing about this approach is that if it works, you actually get the metric. You have some metric that you can try to interrogate. You can like ask questions about how similar people are that you haven't seen before. And to the extent that the metric you've learned generalizes out of sample, this maybe lets you learn something about the human conceptions of fairness for the people on your panel. The cons are that if you want this approach to work, you have to make assumptions about the form of the judgments that the human experts are making. Like in particular, if this approach is going to work, it's got to be that the human judges are making decisions in a way that is consistent with some sort of decision rule that's actually structurally simple. Right? And that's because if you don't make that assumption, there's no way to generalize out of sample. There's no particular reason, if they're not using a simple decision rule, that consistency with sort of the judgments for people you've seen will say anything at all about judgments you haven't seen. In particular, like if you're going to try to do this from the features, you have to assume that the expert's judgment is a function only of the features available to the learning network. Okay, so that's not what we're doing. So we're not attempting at all to learn the metric. We're not trying to learn the encoding of the expert's similarity judgment. Okay, instead, we're going to try to directly learn a classifier that doesn't violate the constraints of the expert similarity judgment more than some bounded amount. We'll have some parameters that sort of give us slack in various ways. And the main pro of this approach is that to do this, it turns out you can solve this learning problem in a generalizable way without making essentially any assumptions at all about the expert similarity judgments. Okay, so we don't have to assume that they're from some sort of simple family. Okay, and from my perspective, I mean, like the nice thing about sort of having fewer assumptions is that it's less likely that they're going to be violated, especially when we're talking about something as sort of ill-defined, I think, as, you know, like people's subjective judgments. There's not a lot of assumptions that I sort of feel comfortable making here. And so, so this is a nice thing that in this approach, it turns out you don't have to make essentially any assumptions. The con, of course, is that you don't get the metric. Like, you don't get the metric as an object to interrogate. You just get the classifier. Okay, so there's some related work, a few years ago we had a paper where we tried to do something similar in a slightly more difficult learning setting, an online learning setting with adversarial arrivals instead of a distributional setting, but and we sort of wanted to give like a polynomial time algorithm, but like the big problem with this work is we had to make very strong assumptions about the form of the human judgments, namely that they were consistent not just with a metric, but with a metric of a very simple form. Okay. Michael and Omer and Guy also had a paper where they sort of gave, they also don't have to make assumptions about the form of these sort of judgments, and they did it by giving a sort of group fairness version of metric fairness using the multi-fairness technology that you heard Guy and Michael talk about yesterday. So essentially that for a very rich collection of groups, the sort of average difference in classification for a pair randomly selected from that group should not differ by more than the average distance between people in that group. Guy and Gal thought about the question of generalization for metric fairness, so sort of an orthogonal problem, although like related to like the generalization guarantees I'm going to talk about, but sort of they're thinking of the metric as given and they're worried just about generalization. And then again, Christina has this nice paper thinking about how you should actually interrogate sort of human beings, right? If your metric oracle is like a human being for the task of learning a metric. So let's sort of now write down a model. So we've got a set of one or more judges, okay? But for this talk, I want to just think about it as one judge to save on some notation. Okay. And like a judge is sort of, the way we think about a judge is as sort of a simple object. The judge is just parameterized by like an arbitrary collection of pairs of individuals that she thinks should be treated similarly. Okay, so for example, if you want to think about these as sort of opinions just about binary outcomes, maybe there are pairs of individuals that she thinks should always get the same binary outcome. Or if you want to think about probabilities, maybe these are sort of pairs of individuals that she thinks should get positive classification with probabilities that differ by no more than 10%. Okay, more generally, a lot of what I'm going to say will generalize to sort of more quantitative judgments, like maybe you actually have an opinion about like how differently it's okay to treat pairs of people. But for the talk and actually for the paper, I'm going to think about limiting this to binary judgments. Okay. And we don't necessarily, and sort of the important thing is this can be like an arbitrary collection of pairs. We're assuming no structure on it. Okay. So we can query the judges about pairs, right? They tell us if a particular pair should be treated similarly or not. And okay, and so now let's think about sort of measures of unfairness given some distribution over classifiers, some randomized classifier. Okay, let's say that let's suppose that the questions we're asking the judges are, do you think that this pair of individuals should be given a positive label or should not be given a positive label with probabilities that differ by more than 10%? Okay, in that case, think about gamma here as being 10%. Okay, so let's say that a gamma violation for a pair, given a randomized classifier, right, a 10% violation for a pair, well, if the judge doesn't think that these people should be treated similarly, then the violation is 0. Okay. If the judge thinks these people should be treated similarly up to some slack of 10%, and in fact, the probabilities of them getting a positive label are within 10%, the violation is also 0. Otherwise, the violation is the degree to which the difference in classification probabilities exceeds 10%. Cynthia.
So P is a,
P is a randomized classifier, so it's a distribution over classifiers.
and the judges can only express the opinion that two people should be treated similarly, not that they should be treated dissimilarly.
That's right.
Otherwise you'd get into trouble. You'd be forcing a triangle inequality or something.
Yeah, I think some of what we say could be generalized to them expressing an opinion that people should be treated dissimilarly, but yes, let's say that the opinions are only that people should be treated similarly, not that they should be treated dissimilarly. So in particular, like in fact, just for feasibility, like the reason why the optimization problem we're going to write down is always feasible is like the assumption is if you treat everyone identically, then it's okay. Okay. So this is sort of the gamma violation for a pair of people.
How do you, what do you do with the more than, this is for one judge. What do you do if you have more than one judge?
Today's talk is one judge.
Today's talk is one judge. More generally, you'd look at sort of more generally, we'd look at the average of this over the judges.
You want to ask a question?
Yeah.
Are the people being judged from the training set or from a separate set, or?
Yes, so we're going to talk about generalization, but we will ultimately have some like training set, which is the only place from which we can get both sort of judgments from the panel and also, like train our classifier. And we're going to be interested in both the accuracy and the fairness in the metric that I'm going to give you in a moment out of sample.
Okay, so this still sort of implies that the metric is simple enough that...
No. So we're not going to need to assume anything about the metric. Which the cost for that is that we won't be able to like answer metric queries, but we're going to be able to guarantee that the classifier still doesn't violate the constraints I'm going to write down. But that is going to be the main thing that the sort of benefit of this approach, as opposed to learning the metric, is that we need to assume almost nothing about the form of the judgments. Okay, so this is the violation for a particular pair. And like in general, our goal is going to be to find some classifier that has low error, subject to the constraint that the expected gamma violation over a randomly drawn pair from this unknown distribution P should be small, less than eta. Okay, so we have two approximation parameters that we can play with. There's gamma, which is sort of like this L infinity constraint, and there's eta, which is sort of like this L1 constraint. Okay. In sample, we're going to be able to make both of these, as close to 0 as you like. Out of sample, it turns out that the thing that you're going to have to relax a little bit is eta. Okay. Okay, so that's sort of the problem. So we can write that down as an empirical risk minimization problem. Okay, so this is nothing other than sort of optimization version of what you saw on the last slide. So what we'd like to do is we would like to find a distribution over classifiers in some class H, okay? And we're also in this the version of this optimization problem I'm writing down, there's another set of variables, which are think of them as slack variables, okay? We would like to minimize error, okay, the error of our learned classifier, subject to the constraint that for every, when I'm writing down this optimization problem, just to make things simple, like imagine that I've queried the judges on every pair of people in my training set. But in general, you don't actually need to do that. You could query a small random sample of pairs in the training set. Okay, but just so that I don't have to write some notation relating to like who I've sampled, let's imagine that I've queried the judges if I have a training set of size n on all n squared pairs. Okay, so the constraints are the following. For every pair of people that the judges think should be treated gamma similarly, I want that, well, they should be treated gamma similarly. The probability that they are classified as positive should differ by no more than gamma. If it does differ by more than gamma, it'll have to be captured in this slack variable, alpha. Right, so this is sort of the L infinity constraint. This is going to fold into the L1 constraint. And this constraint is just saying the average value of these slack variables should be, among people that the judges think should be treated similarly, should be small, less than eta. Okay, so eta and gamma are constants. These are sort of the approximation parameters that you, when writing down this optimization problem, can decide on. Omer.
So I'm wondering if the trade-off here is between the learnability or generalizability of the metric and the utility. But if you can't really know anything about distances for people you don't see, then essentially you just need to assume the worst about everybody, and that comes at the price for utility. Right? Or
Yeah, it's a good question. We haven't thought about that so carefully, in the sense that we've run some experiments that I'll show you at the end, and so you can sort of, for particular people's judgments on particular data sets, trace out what the Pareto curves look like. But
this means that for these cases, the metric was generalizable to some extent.
Maybe, I haven't thought about that.
How they should be classified, just that they should be classified similarly. So
That's right.
So the utility will actually depend on how they're classified.
That's right. So all of these things will interact in a w I don't know how to say anything clean one way or the other about that, but that's not to say that something couldn't be said. I just...
Right. I'm just thinking that if you can't learn anything about if C is really a random collection, then essentially you cannot get anything
that seems
beyond
that seems sensible. So certainly, for some judgments, there's like nothing you can do better than like a constant classifier. Okay. So this is like the optimization problem. Something that's feasible, let's just give it a name. There's these two parameters, call it gamma, eta, subjectively fair, in sample. And our goal, right, we have two goals. One is sort of the optimization problem. We'd like to solve the in-sample optimization problem. And then the other is that show that its guarantees, both in terms of accuracy and fairness, generalize out of sample. Okay. So let's think about those in turn. So, and first, like, what should we hope for? So, it's sort of too much in the way I've set up the problem to hope for like a polynomial time algorithm, because unconstrained learning, like just minimizing error for getting these constraints, that's already computationally hard in the worst case, even for the very simplest of learning problems, just like learning linear classifiers. That's hard to approximate already. But like this is sort of the canonical example of a domain where worst case hardness results have had the least bite. Like these problems are all like really hard in the worst case. You can't, even to any non-trivial factor, approximate the accuracy of the best linear classifier in the worst case. And yet, like we have heuristics that solve these problems very well all the time, right? So for the linear problems and for much harder problems. So we can't hope for like a polynomial time algorithm that's going to solve the problem in the way that I've set it up. But the kind of thing we can hope for is like an oracle efficient algorithm, like some efficient reduction to the unconstrained learning problem. So if you have some heuristic that you believe solves unconstrained learning problems well, then maybe what we can do is, using that heuristic, solve the constrained learning problem via a reduction to like a small number of unconstrained learning problems. Okay, so this is, the framework is sort of, like open to abuse, because these are oracles that solve NP-hard problems. So you could, like write down algorithms that use gadget reductions and solve traveling salesman problem with, one oracle call. But like if you don't abuse the methodology, then it tends to produce practical algorithms. And if I have time, I'll show you a couple of experimental results at the end. Okay, so the kind of oracles we're going to assume that we have are oracles that can solve weighted classification problems. So given a data set, it'll always just be our training data set. We're not going to construct funny data sets with funny gadget reductions. We're just going to assume that we have algorithms that can solve just the standard old empirical risk minimization problem on weightings of our original data set. Okay. And an oracle efficient algorithm is just an algorithm that is polynomial time, assuming it has access to an oracle for solving problems like this. Okay, so brief sketch of solving the computational problem. It uses like my favorite trick. Think about it as a zero-sum game. So you've got some constrained optimization problem, but via Lagrangian duality, you can think of it as a unconstrained min-max problem. Okay, like a game, if you like, played between the learner, the person controlling the primal variables, and the dual player, someone who's controlling the dual variables. Okay, so you just have your original objective, and remember we have two kinds of constraints. We have these sort of constraints for every pair of people. So every pair of people in your training set gets a dual variable, okay? And we have this sort of expectation constraint that gets its own dual variable, and this is now an unconstrained min-max problem. Then we're going to compute an equilibrium of this game, a Nash equilibrium of this game. In particular, the equilibrium for the primal player is just the solution to your original unconstrained optimization problem. By having the dual player play an algorithm like multiplicative weights or gradient descent, any algorithm that has a no-regret guarantee, okay, that you can do efficiently in this case because there's only a relatively small number of dual variables. Okay, so you can efficiently run this algorithm. And we're going to have the primal player play best response, meaning at each iteration, for every fixed value, at each iteration there will be some fixed values for the dual player. The thing we'll need the primal player to do at every iteration is just solve this minimization problem over, he's going to have to find a classifier and some setting for the slack variables. And what you have to make sure you can do is you can, the dual player is always like efficient. The thing you want to figure out how to do is how to use your weighted classification oracle to implement the best response step. Okay, so I'm running short on time, so I won't go through the details, but suffice it to say you can do that. To solve the best response problem, you just have to do two things. One is solve a weighted classification problem with weights that are a function of the dual variables, and you have to set each of the slack variables. But each of those is sort of just an independent, you just have to compute some inequality for each of the slack variables. Okay. And the upshot is, that there is in fact an oracle efficient algorithm that has runtime that's, polynomial and everything you care about. I'm just writing polynomial here, but actually this is just sort of like the convergence bound of gradient descent, so it's not a terrible polynomial. That has error that is sort of equal to the objective that we're trying to compete with, and satisfies subjective fairness that has just a little bit more slack in this L1 constraint. Okay. And the algorithm kind of works, so I'll show you a plot at the end.
And you're assuming here that for all pairs you have the...
So actually you don't need all pairs. You need sort of, it's enough to sort of randomly sample something like VC dimension many pairs. So you don't actually need quadratically many pairs. It's more like linearly many pairs. Okay. Let me just say a little bit about generalization, which is mostly standard, right? So there's nothing complicated going on here. If I look at the empirical fairness loss for a particular classifier, right, which is just the average over all of the pairs in my data set of this gamma fairness violation term, this is, it's like a 1 in n sensitive function, right? Because if I change one data point, I can change n terms here, but there's I'm dividing by n squared. So by McDermott's inequality, this thing exhibits Chernoff-like concentration. For any particular classifier, it's extremely unlikely that on two samples it would have a very different fairness loss. And so by sort of like a standard like two-sample trick and Sauer's lemma, I can get uniform convergence over all of the deterministic classifiers in my class with a sort of sample complexity that depends only on the VC dimension of the class, okay, for this fairness loss. The only complication is that this is sort of uniform convergence over just the deterministic classifiers. For error, that would be enough to get uniform convergence over the randomized classifiers as well. Here, the fairness loss is not a linear function in the mixture weights if I have a randomized classifier. So it's not enough, but it's not too hard to get around that problem. Once you have uniform convergence for the deterministic classifiers, you can take an epsilon net over the distributions and have union bound over it. Okay. The upshot is that you sort of get the same statement, but now with out-of-sample bounds. So there's an Oracle-efficient algorithm. It's got sample complexity, committee complexity, like the number of times you have to like ask someone for a pair, and running time, that's all polynomial in the parameters you care about, that finds a distribution over classifiers that competes with optimal and is subjectively fair with a little bit more slack on this L1 constraint, but now out of sample. Okay, and we didn't have to assume any structure on the judge's preferences. No.
Sorry, can you remind me in what way is it opt?
So this is just like when I wrote down the like empirical risk minimization problem, this is the error of the minimal error classifier that satisfies gamma eta subjective fairness on the distribution.
And the error is, yeah, okay.
Just classification error. Okay, so I don't have too much time. We ran some experiments. We used the COMPAS data set. Well, okay, it's not enough to have a data set in this setting. We have to have like human judges. So our human judges were 43 undergraduates from some major American research university. They had just taken a course on they had just taken a course on algorithmic fairness. These are extremely preliminary. So like, there's lots to complain about these experiments. The main takeaway is just that you can run the algorithm. So yeah, so for sort of the COMPAS data set, we showed each judge 50 randomly selected pairs, right, the data points from the COMPAS data set. We showed them the features, which are things like gender, age, race, and then statistics about their criminal history. We consciously did not show them the outcome, because otherwise you'd think they would just suggest that you should classify people similarly if they have the same outcome. Okay, and then from this data, we like ran our algorithm. Okay, so there's like a couple questions you could ask. Maybe the first one is just like, does the algorithm even work? We have like a theorem that says it works assuming that you have an oracle for unconstrained learning. Of course, we don't have an oracle. We just have a heuristic, something based on linear regression. Okay, but it seems that the algorithm works. So here's sort of a simple convergence plot. What you're seeing is the iterates of the algorithm as we run it. On the x-axis is the error of the classifiers at each iterate. On the y-axis is gamma, the sort of maximum fairness violation term. Here we set like eta to be 0, and we set gamma to be 30%. And what you see is that the thing seems to converge. That is, it starts at the sort of unconstrained error optimal thing, and then it seems to sort of come up exactly to this target gamma parameter.
What's gamma again?
30%. Oh, it's the when someone is said to be, you know, what is treated similarly mean their classification probability should be within 30%.
And what was eta?
The here eta is 0, so it just means for every pair. Okay. You can draw Pareto curves for different undergraduates. They're different, so people don't have like a consistent notion of fairness when you ask them questions like this. There's some other stuff you could do. We haven't done it yet.
How transitive were they? So if the students said that A should be treated like B and B should be treated like C, what was the chance that they said A should?
Yeah, that's a great question. That's one of the things we haven't done yet, but it's, with better data, that's definitely a question you could ask. So we have only very preliminary. The algorithm sort of works. You can run it, but we don't know. We haven't done much to interrogate like human notions of fairness, although that's something you could conceivably do. Okay. Thank you. There's a paper on archive.
Maybe one quick question while Swati sets up. Lee waits first.
It seems like the judgments can actually be pretty manipulated depending on the data that you expose to the judges to define similarity. So I guess practically speaking, is it not still the same issue of having to decide which attributes to show the judges in order for them to make their call on how similar different people are, and could you not manipulate the process at that point?
Absolutely. So there's certainly all sorts of experimental design questions that we haven't even attempted to think about yet. That's something we're interested in, but we haven't done yet.
Okay.
Maybe one more question.
Maybe this is related to this, but, and I hope I didn't miss anything, it seems like this elicitation is, especially in groups, possibly not incentive compatible.
Well, the people that we're eliciting from are unaffected by the outcome. So there's not a natural notion of incentive compatibility. It's not clear why you, as the undergraduate in this class, would have any utility for.
Maybe the things are great.
Not in this case.
Not in this case. Yes. The people who the outcomes affect are different from the people whose preferences we're eliciting.
It seems like the judges do have preferences over what goes into practice, maybe through social preferences or caring about some state of the world or something. In any event, I'll take it offline.
Let's take it offline.
All right.